Thanks. My name is Paola. I'm a data scientist at Silke Engineering, and in the next 20 minutes, I would like to talk to you about a cool project that we had at Silke roughly last year. So the client for this project is called PDR Team. They are a German car repair company. So basically, you drive your car to them, and they would fix any dent you have on your car bodywork with these tools. And you can imagine if your car was, for example, under rough weather, like a strong hailstorm, you might have like hundreds of these little dents. And since, unfortunately, they don't do it for free, they want to charge you for their service, they need to assess how much the price would be. And for doing that, they basically go around the car and count manually each of these dents. And this manual process it usually takes roughly 30 to 40 minutes. And they basically came to us and asked us to automate this process so it would be cheaper. And basically, they want a solution that counts that estimates the number and the size of the dents around the car per car part, that still has a good accuracy, and most importantly, that reduces the time for the original 40 minutes down to 5. And we had 3 months to come up with a prototype for this. So the requirements were quite ambitious, but PDR team came prepared. They already developed an arc structure, this that you see on the left, called Colibri, that has 8 light stripes and 7 cameras all around. And I hope the videos work. Yes. And you see when a car drives under it, the stripes, the light stripes, kind of bend around the dents. So it's much easier to see where the dents are when you have a video coming from this. So this is basically our data for a project. So now comes the first technical issue. We have 3 car types with 3 different colors. But we only have 1 video per car, and that's all the data that we have and we can work with. So because of this, it's already kind of hard to do stuff like learn the shape of your car. So we decided to have something that would help us. We decided to use some markers on the car, and those would basically help us map the shape of the car. These are Aruco markers. They are very easily recognizable in the image. You can just do it with the standard library. And there you get the ID and the position of each marker, so you know exactly which part of the car you are looking at. Another simplification that we did, mostly because of the short time for the project, was to not use all 7 cameras, but only 3 of them. And in this way, we could assign each part of the car to only 1 camera, because otherwise we would have the issue of having 2 cameras seeing the same part and maybe counting the same dent twice. Lastly, still because of the time constraints, we decided to outsource the labeling. So we had a partner that labeled each frame of the video by drawing bounding box around the dents. So this is basically the skeleton of our solution. We have 4 steps. First, we extract the single car parts to work with. And we do that with the help of those Aruco markers. Then on each car part, we detect the dents on the frames of the video, on the single frames. Then in a third step, we aggregate those detections in a global view, and finally we process this view to merge overlapping detections and make sure that we don't count the same dent twice. So for the frame detection, we used a pre-trained RCNN, and we fine-tuned it with the one video that we had. And we gave the inputs for this tuning were chunks of this image, and we made sure that these chunks kind of overlapped. And this is just because we might have, if these are the labels, we might have something on the border, and we don't want to miss it. So if they overlap and something is on the border, it will still be in some other chunk. Yes, as I said a couple of times, the fact that we had one video per car was a bit of a problem. And one of these problems was we couldn't really evaluate the model if we just used it for training. So for example, doing hyperparameter optimization was kind of hard. So we had to be a little bit creative. We thought, well, the two sides are kind of symmetric, so maybe if we flip one of them, they kind of look like the same of one side, and we can use one for training and the other one for test. And for the top view, we did basically something analogous. We cut the image in half, and we flip one of the half, and then we have one for training and one for testing. Also, we realized that during training, this Aruku marker sometimes kind of look like the reflection of the light, so they might be mistaken for a dent. So we had to mask them before feeding them to the training. Yes, and we did some standard augmentation also. So this is this would be the result of the single frame detection. So you can see the same dent is detected in multiple frames, sometimes in subsequent frames, sometimes it disappears and then appears a little bit afterwards. And also, the shape of the car kind of changes a little bit if it's directly below the camera or if it's at the end of the frame. So it's not so easy to aggregate these detections. But since we have the Aruku markers, we thought we would kind of exploit them as much as we could, and we decided to use them to basically create a global mapping of it. So we have one marker of reference, and we calculate the average distance of the other markers, and this gives us a reference coordinate system. And then whenever we get one detection, we basically express that detection as a linear combination of the markers around it. And that way we can remap it on the global system. And even if when the car moves, that part kind of changes its shapes a little bit, the triangle it is in will also change accordingly. So the mapping is somehow consistent. Yes, so once we have this aggregation, we can do a heat map of the detections that we have, and we want to basically detect the dents that were the same but detected in different frames. So to do that, we fit blobs over it. And basically, the number of blobs is now our estimation for the number of dents. And from the diameter of these blobs, we can get the original size. And this is the video that displays the global detections. I hope that it. Can you see the purple? Okay, good. Yes. And yeah, so sometimes it kind of flips a little bit. That's because the markers appear in the frame, so it's readjusting. It's not, as long as the markers are outside, it's kind of predicting where they are by the global view, and then when they get into frame, it readjusts it. So this is actually only a prototype, and in order to have a commercial solution, there's quite a few things to fix. One of them is to introduce the remaining cameras, because some of the parts either are not visible, or if they're visible, the light reflection doesn't hit in the right way. So it's those parts are not really covered. And when doing that, we would have to handle the overlapping view, of course. Another issue is that we have a lot of markers at the moment on the car. So it's like around 100. So that's, of course, not feasible for the final usage. So yeah, we will need to reduce those. And one way would be to have more data in order to train an algorithm that allows us to learn the shape. And also, more data would definitely be required in order to have reliable metrics, because we don't really have a test set at the moment. Yes. So before finishing, I would like to quickly go back to the time constraint. So that was one of the hardest constraint to fit, because we had like this very big video files, and we had to do something to reduce the processing time. So one thing we did was in the frame detection, we restricted the search to the parts that were covered by the markers. So we don't feed chunks of the whole image, but only the parts where the markers are. And another thing that helped massively was the decision to deploy the solution to the client's machine in a series of microservices, for that were deployed in their own Docker container. And this way we could parallelize a lot, because, for example, processing the roof or the door is completely independent. So we could parallelize that. And also creating the resulting video that was also very heavy computationally, and we could parallelize that. And everything communicates with Redis queues, so that was also to ensure that this division in microservices wouldn't slow down the final application. Yes. So since I showed the Mazda video in the examples, I will finish with another one, the Suzuki video, and in the meantime, I can answer any questions you have. Thank you.
Good, we have time for a couple of questions. Is there any? There's a question over there, there's a mic coming.
Thanks for the interesting talk. What about the size of the dents? Does it matter with respect to the repair costs, and how would you approach it?
Yes. So we needed to also estimate the size. So we did it, we estimated by looking at the diameter of the blobs that we had on the matrix. And of course, that diameter alone doesn't tell us anything, because it depends also by the distance. But we have the Aruku markers, and we know the real size of the Aruku markers. And we can see how big they are in the image. So basically, we do the same proportions to get back to the real size of the dent.
Other questions? Does not seem to be the case. Thank you very much. You also have a booth upstairs?
Yes, we have a booth upstairs if you want to ask more questions or ask us about other cool projects.
Excellent. Thank you very much.